All right, we're looking at section 3.2, and notice that it's starting out there with saying that the arc length, that ratio, they're saying the arc length is to the radius as the central angle in radians is to 1. And then from that, they're going to get this formula where the arc length is equal to the radius times the central angle, and theta has to be in radians. So remember put that central angle in radians. Don't put it in degrees. And they're telling you that's the common error. He's using the formula and then trying to put degrees in here rather than central angle in radians. And then the other formula that is, it's for this is arc length. All right. That's what this is. And then the area of a sector. And they tell you like a pie-shaped element. And that area of a sector is area equals 1/2 r squared theta. And once again, this theta has to be in radians. And then they're saying that theta is that sector of that circle. And once again, remember to do it in radians. I don't have it. I forgot to bring it with me. I didn't set it in here. Well, when I get through today, I'll try to be sure and put it so I can get it Friday. All right, so let's look at problems. They're on section 3.2. And what we'll do is they're just saying it's a concept check. It says find the exact length of each arc intercepted by the given central angle. So number 2, remember that arc length equals r central angle in radians. So in number 2, you just substitute for r the 12 and then pi over 3. And prefer that you leave that in that form, because then that's exact. And then the next one is to find the radius of the circle, that next group of problems. So if you're going to use that same formula, S equals r theta, but you're going to find the radius, so r is going to equal the arc length over the central angle. And the S is going to be 14 pi, and then the arc length is 7 pi over 4. So you invert and multiply. And this goes out, that makes it 2, and you get 8. So 8's the radius. And then the last one is just using the formula for the central angle. So you're going to use this formula, solve it for the central angle, and then we'll put the values in. Arc length is 6, and the radius is 4. So the central angle is going to be 1.5. And we can, that's accurate. So that would be your central angle. It can be, this is going to be exact. It can be 1.5, or else it could be 3.5. It won't make any difference there, because this is accurate. You know, it's not a rounded off value. All right, so the next group of problems says find the length to 3 significant digits of each arc intercepted by the central angle theta. So L, and we're using the formula S equals R theta, and we just substitute into this. The R is 0.892, and the central angle is 11 pi over 10. And this says that it's going to be 3 significant digits, so you're going to have to put it in the calculator to do this problem. Wait, 892. Divided by 10. Now, because it's, I don't know why I put minus, the wrong thing. Hit the wrong button. Well, that's still the wrong button. Divided by. Okay. Being it's all multiplication and division, it does not make any difference which order we do it in. So it says 3 significant, so that'd be 3.08. That would be our answer. Now if you do 16, R is 1.9. Then you'd have to do 135 degrees, and then you got to change that to radians. So you'd go pi is to 180. Because the formula is good only in radians. So then you'd have to put that in like that. So remember to do that. And I did something wrong. Somehow I got a negative sign up there. So that should be an arc length of 146. I don't know what, I must have got that silly thing. Must have hit E in that. That'll make a difference, probably. No, I don't have any other extraneous things in there. So that's 53.
You forgot pi.
Oh, I got E. That's how come. I put E in rather than pi. Okay. So I gotta go. Times. I got pi in there. I gotta go second insert. The division sign. Just well. The insert isn't gonna work. Now the insert's working. No, I think I got it. 169. All right. The next thing is concept check. It says find the area of each sector. So what we're going to have to do for the area equals 1/2 r squared theta. And then this formula that S equals r theta, theta equals S over r. We're going to have to utilize that because notice that it's giving us 4 pi, that S is 4 pi, and that r equals 8. So it's not giving us theta. So we're going to have to substitute in for this theta. And this is actually the formula we're going to have to use. For theta, we're substituting S over R because it's giving us arc length. And we have 8, 4 pi over 8. Now it depends upon what we want to do. I could do this, then do this is, I guess I could make this 4. It was 1/8 left. So this is 16 pi. And then if I wanted to get, this is accurate. So this would be area. So you're going to have to use this formula to put in there. Otherwise you're not going to get that because it's giving you arc length. It's not giving you that central angle, and this formula is giving you in terms of central angle. You want to? That's enough to do those 39 through 42? I mean, that's the same formula. Now it says find the measure in degrees of each central angle. The number inside the sector is the area. So 44. We're going to be using this area equals 1/2 r squared theta. And they want the area of the central angle. So they want to solve this for theta. So theta is going to equal multiplying both sides by 2 pi over r squared. And then they want it in degrees. So what we're going to have to do is take this 2a over r squared, and that's radians, and then do 180 over pi. And that will get us degrees. So we got 2. They give us the area as 96 pi. R is 12. What's that? Oh, this should be squared. You're right. Okay, so the pi goes out. I think one of the 12s goes into 96, don't it, 8 times? And 2 into 6 times. 6 into that 30 times. I think that's about as much reducing. 240 degrees. So that should be the amount of degrees, because that's what it wanted, a number. Find the measure in degrees of each central angle. Now, the next one says find the measure in radians of each central angle. The number inside the sector is the area. So this is just going to be this formula without the conversion factor. We start out with this. And then we get theta. And we substitute 2 times 8 over 4 squared. Well, one of them 4s goes into 8 twice. This one into there 2 times. 1, huh? 1 another 8. So that should be 1 radian. Okay. It says find the area of the sector of the circle having a radius r, central angle theta. Express answers to the nearest tenth. So just substituting into the formula. Do 50. 1/2 r squared. Now notice this one's in radians, so it'd be appropriate just the way it is. 90 squared by 5 or 6. Okay, so 6 goes into one of those 90s. 90 to the first, and one of them would be, what would that be, 15. 2 goes into the other 90, 45. And that's pretty big. That's 15 times. I don't know. This is a pretty big number. that what everyone got? What'd you get? 33.
It's 45 times 15 is 670.
Oh, here. I got 15. Yeah. 30. Yeah. So then this is 337. So that should be it. Then 52. What's the area? But it's going to give us degrees, so we're going to have to do our conversion here of pi over 180. R is 18.3. Looks like a calculator problem to me. Looks like I entered it right. 365. I what? 365. Is that what everyone got? $365. Okay. So any questions on that? It's just using the formulas. You just gotta plug the values in. Okay, the next section there is the unit circle and circular functions. The circular functions, the unit circle, what they're talking about doing is taking and however we want to do this, but have this radius be 1 unit long. This from here to here is 1 unit. And then let's see. Then what I'm doing is I'm taking this circle right here, and then this is 1 unit, and then do do the trig functions on that circle. So what you do is, if you look at the bottom of the page there, this is the central angle and this arc are going to be the same, because that ratio says S equals R theta. So if R equals 1, then the arc length equals the central angle in radians. So this central angle is going to equal that arc length, and so the trig functions on a unit circle are equal to the trig functions of the central angle of the arc length. So what we're doing is we're doing a distance here on the unit circle and get a trig function that's equivalent to the central angle trig function. So if we have 30 degree central angle, then we have a central angle in radians of pi over 6, but we got an arc length that's pi over 6 long. Same thing on a unit circle. So, and then at 45 it's the same, and then 60 and on around. So what you do is you have the sine of pi over 6 on the arc length of the unit circle is equal to the same as the sine of 30 degrees, and the sine of the central angle in radians of pi over 6, which is 1/2. And that's and what it is, the unit on the unit circle right here, this distance right here is 1. And if we drop a vertical line down, this distance right here is 1/2, and this distance from here to here is the square root of 3 over 2, and that's the cosine of pi over 6. So the XY coordinates are actually on the unit circle are actually the cosine sine, because this coordinate right here is square root of 3 over 2 1/2, and that is cosine of the arc length times the sine of the arc. Oh, not times the sine, cosine sine of the arc length. The central angle, I guess I could do it this way: arc length S, arc length S. So on a unit circle, that's the ordered pairs of the point are the cosine sine. And that unit circle, those values, that 30 degrees or pi over 6, 45 degrees or pi over 4, pi over 4 radian central angle, or pi over 4 distance on the arc, and this is 60 degrees, pi over 3 central angle, or pi over 3 arc length, and then this one is 90 degrees, pi over 2 central angle in radians or pi over 2 arc length. And then all the ordered pairs cosine sine. Those are things that you should memorize. Because that, notice that unit circle, it's all those increments of 30 degrees and 45 degrees. And it's not too hard to do, because if you notice that it goes from 30 degrees, sine starts out at 1/2, goes to the square root of 2 over 2, square root of 3 over 2, 1, then it goes here, or square root of 3 over 2, square root of 2 over 2, 1/2, and 0. And the cosine starts out at 1 down here, goes to square root of 3 over 2, square root of 2 over 2, 1/2, 0. Then you're going to go a negative 1/2, negative square root of 3 over square root of 2 over 2, negative square root of 3 over 2, and the negative 1. And so you know, just all those numbers just repeat. You just have to know where it's at. And then what we're going to do with this is this arc, as it goes around, we're going to take it, set it at 0, and roll it out. Then we're going to graph those distances and show a sine wave, and then a cosine wave. And we'll look at tangent waves, cotangent waves, secant, cosecant, and so on. So, any questions about that? And you know, this is used if when you do a heart rhythm is called a sinusoidal curve. Sinus rhythm. It's a sinusoidal curve. What it is, a heart rhythm, when you graph it out, you know, it's something that generally goes up, comes down, and goes up like that. And that's a sinusoidal curve. And that's why they call it a sinus rhythm, because it's a trig function. And your heart impulses are converted to digital readout. And it becomes then sinus rhythm. And then all these curves are called sinusoidal curves. And if you have oscilloscopes, as we get into it, oscilloscopes will do things, and you will see all the different curves happening. You'll see things where they go from sine curves to cosine curves to tangent curves to cosecant curves and so on. Yeah, Corey. How's that? Yeah, it's a sinusoidal curve. An ocean wave is sinusoidal. It's a diminishing sinusoidal curve. You know, an ocean wave, theoretically, if you throw a rock in the ocean, that curve goes until the other shore. It just gets so small you can't see it anymore. That's theoretically. You know, an ocean wave is sinusoidal, but you know, if you throw a rock in the ocean, it starts out doing something like this, but then it comes down and gets smaller and smaller and smaller, but it never really goes away. It approaches the horizontal infinitely close. So you can get as close as you want just by going far enough away. And it's sinusoidal. That's in theory. Okay. On the next page there, on page 120, they're talking about, because the x and y values are in a unit circle, x squared plus y squared equals 1 in the unit circle, then the x value is sine, right? So sine squared of any angle plus cosine squared of any angle, or arc length, is equal to 1. And then the sine is always going to go from -1 less than or equal to the sine of your angle, which is less than or equal to 1. And the same way with cosine. And on the next page, they're talking about the domain of these functions. The domain is what is this limit on this central angle, and there is no limit. It goes from negative infinity to positive infinity because it goes around and around in either direction an infinite number of times. Now the tangent and secant functions, because the tangent is y over x, or sine over cosine. This thing is undefined wherever cosine is 0. And cosine is 0 the cosine is 0 when theta is pi over 2, 90 degrees, right? And then it's cosine at 3 pi over 2. And then 5 pi over 2. And so on. So if you're going to have the cosine is going to be 0 whenever you're in this position or in this position, right? That's where your x value is 0. And as you get close to it, the y value is going to go to 1 and the x value is going to go to 0. So what is the tangent going to go to? When the denominator goes to 0 and the numerator goes to 1, what's the combination of the two? It goes to positive infinity up here, and it goes to negative infinity down here. And so it's called an asymptotic at that particular point. So if you're graphing it in 2 dimensions. And notice that when in that particular thing, when they're describing this thing, they're describing this as the arc length. The arc length such that S cannot equal and 2 times any integer is what? A positive, right? You add 1 to it, you get positive. Is an even number. 2 times any number is an even number. You add 1 to it, it gets an odd times pi over 2. So it's 1 times pi over 2, 3 times pi over 2, 5 times pi over 2. It's not an even. It's not pi or 2 pi or 4 pi or so on. This has got to be an odd number. So they're saying that whenever that happens, then this is going to be undefined. And then they're talking about cotangent and secant. Now they're the other way around. They're not defined here because that's where the y is 0, nor are they defined out here. And cosecant's 1 over sine, so secant being 1 over cosine, so it's the same as tangent. So they're just telling you where it's not defined at. They're warning you on the bottom of page 121 you have to put your calculator in radian mode when finding circular function values. So whenever you're doing these circular functions, you're going to have it in radians because you're actually doing arc lengths. On page 123, it's saying determine the number with the given circular function values. And notice there's a, remember that the keys marked sine inverse, cosine inverse, and tangent inverse do not represent reciprocals. This is what they're telling you. Don't think that, don't get this, sine inverse of x equals theta. What this is doing, don't think that sine inverse x equals 1 over sine. It's not true. But what there is, when you do the sine function, you're doing the sine function. This is what you're doing. You're doing 4 arc lengths, y equals sine. This is the y value, which is the sine of whatever this arc length is. And that's the way I'm going to do it. If I have 0 arc length, the sine is 0. If I have an arc length of pi over 6, the sine of pi over 6 is 1/2. Right? If I have pi over 4, and I do the sine of pi over 4, I get the square root of 2 over 2. If I have pi over 3, the sine of pi over 3 is the square root of 3 over 2. And if I have pi over 2, the sine is 1. So what this is, this represents an ordered pair of theta, sine theta. And these ordered pairs are, for the first one, 0, 0. The second one, pi over 6, 1/2. The third one is pi over 4, square root of 2 over 2. The next one is pi over 3, and the square root of 3 over 2. And that's pi over 2. These are the ordered pairs. Now, if I do an inverse function, then what I'm doing is I'm inverting these. I'm changing these positions. I'm putting the sine of the angle first. Notice sine of the arc length first, and then the arc length. So this one's still 0, 0. But this one is 1/2 pi over 6. And this one's the square root of 2 over 2 pi over 4. And this is square root of 3 over 2 pi over 3. And this is 1/2. So this is actually sine inverse of this. That's what this is. So if I say the sine of my central angle in radians or my arc length is 0, then I have an arc length of 0. If my sine of my arc length is 1/2, my arc length is the square root of pi over 2. That's inverse function. You say what the sine is, and then tell the arc length. Here is arc length, give me the sine. An inverse function is what is the value of the sine, what is the arc length. That's an inverse function. You're interchanging the x and y. When you do 1 over, then you would do theta, and this would be 1 over 0, which would be undefined. This would be 2. This would be 2 over the square root of 2. That's not what it means. It means you interchange the x and y's. That's what inverse function is. So what we're going to learn is that we have to restrict the function to get inverse functions. You can't, you can have, and I've told you this before, you can do the sine of some multiple of 30 degrees. And you can get a value, but you don't, when you do the sine inverse of that value, you won't necessarily go back to the angle you came from, because it's restricted to wherever it's 1-to-1 the function is. And we'll talk about that. Okay. Corey, homework? What? Your what?
I said, thankfully my notebook was laying on the bench inside, like by my back door, and in the outside.
And you got both of these?
Yeah, the other one was stayed. Last week I couldn't remember if I had
Evil stuff.
just forgotten to make it inside, or if I had like put it
That's
on
why I don't
the
take
car and
credit.
stick the other stuff in the car, and I just drove out with it on top of the car.
I
Had me a little
think
worried.
this imaginary number. Sine, cosine, tangent. Don't take credit.